Okay, we're recording now, right? I don't know, my computer is acting a little weird. Okay, good morning again to anyone who is here and who is watching us offline. This is lecture 13 in high dimensional probability. Okay, so where are we now? We have very good examples of results about specific distributions, such as normal distribution or Bernoulli distribution, Hövding's inequality, for example, Chernov's inequality. They're very specific, though, right? There's Bernoulli distribution, nothing else, and sometimes that's enough for the graphs, for example, right? We had this beautiful example of random graphs where Bernoulli distribution arises naturally. It's just there is edge or there is no edge. Fine, it's a very, very discrete. And sometimes there are examples where normal distribution arises naturally. But more often than not, you have some general situation. In data science, let's say you want to prove that some algorithm works. You want to prove guarantees for the algorithm, and you want to say, my algorithm will work for any kind of data. Right? Well, that's too optimistic. It's not like, it's very hard to find something that works absolutely for any kind of the data, even if the adversary plans something like all these little outliers. So we put model on the data. We say it will work for nice data, for the data sampled from a good distribution. Okay. Now the question is, what is that good distribution? Right? What is the kind of a default distribution to go? Just like you say, okay, normal distribution, Bernoulli, but this is too restrictive. So what is this class of distributions for which data scientists are content with proving the theorems for? And this is the class that's called Sub-gaussian distributions. Most of the theorems now, if you prove for Sub-gaussian distribution, your result, if you prove that the algorithm succeeds for any data drawn from a Sub-gaussian distribution, people say, good, that works. And of course, somebody asks, can you extend it further? But that's only generates a dialogue. But the main point is that Sub-gaussian distribution is the kind of the very good class that, on the one hand, it's general enough, it encompasses Gaussian, normal, and Bernoulli, and many other distributions. So people are okay with like, whenever something works with Sub-gaussian, people expect it to work in general, I guess. And on the other hand, it is a class that's that we say Sub-gaussian distributions, they inherit many useful properties of the Gaussian. So you're like almost cheating, like you're almost working with the Gaussian, but automatically you know that you work in much larger generality. So what properties? So useful or maybe nice properties of the normal distribution. What do we want to have in general? So yet nice properties. For example, tails are super nice. We know that, right? This is a Gaussian tail bound that decays super exponentially. So this is a familiar picture where the little tails here contain very little probability. So very fast decay, nice. Second, the moments. So if the moment is absolute moment is this. Okay, and if you take the pth root, that becomes the norm. So I should mention that name, the tails. Okay, and then second, the moments, which we capture by the notion of the LP norm, they should increase, they always increase, and they increase to infinity, unavoidable, but not like crazy, polynomially fast, like square root. Okay, what else we proved? For example, last time we proved something like this, expected value. If I put here g squared, exp of g squared divided by 2, that will not be good. Because imagine what happens, just think, so that you'll integrate this function to the x squared over 2 against the Gaussian density. They will kill each other and the integral will diverge. Right? So this you can't expect that to be nice. But if you make like g squared over 4, that will be okay, like because you will integrate slightly smaller quantity against faster decaying. So that's okay. And then we checked, I think, last time that it was less than 2, for example. Good. And what else? The moment generating function looks good to lambda g is I think equals to it square over 4, maybe lambda square over 2. I think it's true that thing. So these are all little nice things that help us if we have a normal distribution. Okay, where are we going with this? So big surprise. So we'll show today that all of these properties, 1, 2, 3, and 4, are actually equivalent for any random variable. They're telling us exactly the same story, although it may look like they're telling us, okay, something about tails and moments, and they're telling us exactly the same story. It's one thing that they're telling us. They're equivalent for any distribution. And once we realize that, we'll just call that distribution Sub-gaussian for the obvious reason. It's Gaussian, or maybe even better. And that will be the content of today's class. Okay. And then we will just stick with the Sub-gaussian distribution because we have so many good things about it that we can just prove our theorems one way or another. Okay. Okay. So make this in red, maybe. So for any distribution, not just normal, these properties are equivalent. Okay, so let's state this formally. Let's call it a Subgaussian lemma, just so we have a name in the future. Subgaussian lemma. And it will say that for any random variable x, the following are equivalent, and this is abbreviated TFAA. The following are equivalent properties. First, the tails. And I'm just kind of almost copying this from here. Except we may allow some freedom in the choice of this constant 2. The 2 is probably not important, so we make a little freedom here. Minus 2e minus t squared divided by, and let's make another constant, k1 squared for all t. Let's say there exists k1 so that this happens. Okay, so we make a little bit of a room to wiggle. Second, the moments. The LP norm, and here I'm copying, almost kind of trying to copy this. Now the LP norm of x is bounded by root p, but maybe we again allow some room here, k2 maybe, root p. So there exists k2 so that this happens for all p. Okay, third, we're looking at this, and similarly, say that expectation of x squared. Again, let's allow some room. Maybe not just 4, maybe some constant there. X squared divided by k3 in this case squared is less than 2. Okay, so far so good. Okay, equivalent. Now you have to be a little bit careful here around the MGF. If you ever remember what MGF really stands for, moment generating function, right? How it generates moments, in particular the first. Okay, how does MGF generate moment? Does anybody remember? Let's say expectation. How can you read the expectation of x from this function? Let's say this is my MGF. How do I know the expected value of x? So if I know this function in lambda, this function of lambda, then for example, from just by looking at this graph, I know that expected value is positive. How do I know that? Moment generating function generates moments. How? You know that, someone knows. Differentiate. First derivative gives you the first moment. Second derivative gives you the second moment. There's going to be some scaling, like 2 factorial, 3 factorial, but so fourth derivative is fourth moment. So if you differentiate it once, then you get the first moment. And in this picture, I see that the first derivative at 0. The first derivative at 0 is actually positive, and so that's expectation value is positive. Okay. So where I'm going with this is from the way this looks, e to the lambda square over 2. That looks like this. And so the expected value, which is the slope, is going to be 0. It kind of indicates the expected value is 0. So we're going to throw this extra condition that expected value is 0. So moreover, which is actually true for Gaussian, it's true, but we don't know in general. So moreover, if the expectation is 0, then these properties are equivalent to the fourth one, which is the MGF, moment generating function. Lambda x is less than, and here we again allow some room, let's say k4 squared, lambda squared. Okay, so that's our lemma. Basically says that all this story about normal distribution, all of its properties, they actually are the same. They're telling us the same story, and that story we call Subgaussian. So a random variable x that satisfies 1, and therefore all of these properties 1 through 4 is called Subgaussian. Good. Good. And we say sub-Gaussian because it could be even better, right? Maybe the tails are even better than this. We have just inequality. Maybe the moments are even smaller, and so on and so forth. So let's say if you take a random variable, which is sub-Gaussian, and then multiply it by 1/10, it will be automatically sub-Gaussian. So the smaller it is, the more chance it is to have sub-Gaussian property. Good. All right, so now we'll prove this. And in fact, the proof is very instructive. The proof actually is maybe more interesting than the result itself, because it kind of teaches you to handle all these different ways the random variables behave, different properties. Okay. The proof is based, okay, let's see. So let's think from first to 2, from tails to moments. Let's even think from tails. If I know something about tail behavior like this, let's say first moment, the expected value. How do we know, well, for p equal 1, let's say, forget absolute value, expected value. So how do we, from the tail behavior, if I look at the tail of the PDF, then I will know that my expected value is small. How do we do that? And this is a useful tool that we will use here. It's called integral identity. Probably you have not, maybe you have not heard of it, but it's an amazing identity that holds for any non-negative random variable x And it is a formula for expectation. Believe it or not, it's very very powerful formula that just says that expected value is the integral of the tails. That's it. For any non-negative random variable. So if the tails are small, the random variable is kind of more compactly supported around 0. The expectation is small. It kind of makes sense. But what's surprising is it's such a simple formula holds. Do you have any questions about the statement of the formula, or we're good? We'll prove that formula first and then. Good. Okay. Okay, so here's how you prove it. First, in a trivial way, we can express a number as the integral, not expectation, but then we'll put the random number here. So x, just take any x and express x as the integral in this trivial way from 0 to x dt. Right, okay, clear. Now, I would like to change the integral to infinity because that is what we're heading to infinity, but then I have to truncate it. So I'm integrating the function that is the indicator function like this. And by this, I just mean the indicator function that takes value 1 or 0, depending if t is less than x or not. Yeah, so it just kills the integral after t, and of course it's the same after x, and that's of course the same. Okay. Good. And then we take this formula, substitute the random number for it, x equals x, and take expectation of both sides, on both sides. So we get x equals the integral of this thing, dt. Then we take expected value. I take expected value on the right side too, and we can move it inside the integral. I can interchange expected value and the integral. Why? Why is
because it is non-negative.
Yes.
And using the Fubini's theorem.
Exactly, exactly. By Fubini theorem, that's true. Perfect. Fubini-Tonelli theorem, actually, because it's Lebesgue integral. One of them is Lebesgue integral, but yeah, Fubini. Good. So what's that? What's that thing? Expected value of the random variable, which can only take values 1 or 0.
Probability of 1.
Probability of 1, exactly. Exactly. So this is just a probability. Just think of it, it's what's expected value? It's value times probability plus value times probability plus value times probability. Well, then one of the values is 0, so we don't think of it. And the other value is 1, so it's 1 times the probability that t is less than x. I should have. Yeah, I think it's it. That's it. Yeah. Good. Done. Proved. Yeah, that's a useful formula. Any questions? Good. And then we prove the Sub-gaussian lemma, which is this. Let's prove first 1 to 2. Okay, that's going to be fun. Let's see, 1 to 2. So if we know the tail bound, then we know the moments. For the first moment, which is expectation, this is basically the integral identity. That's what it is for, right? Just take absolute value of x and run the integral identity, and we'll see what happens. But then we have different bounds. So let's do that. Just for simplicity, let's forget about this k1. Let's assume the k1 is 1, just to keep the formulas easy. Then you can throw it in. Okay, so we need the moments, expected value of x to the p, and we express it as a tail. Well, so we run this formula, integral formula. So we get this integral, apply the integral identity, not for x, but absolute value of x to the p. Still a random variable, obviously. Good. Perfect. Okay, so what do we know? What do we need to know? We know tails for x, and here's the tails for x to the p. So it makes sense to change variables. So let's make the change of variable t equals s to the p. Understand why, right? Because I want x greater than s. Okay. Change the variable, so dt is ps p minus 1 ds. So the limits of the integration are still the same. So x to the p is greater than s to the p, take the pth root, ps to the p minus 1 ds. Cool. Okay, now this tail we know. All right, this we know, and let me show it to you one more time here. This is 2e to the minus t squared. Remember, if we decided that k1 is just kind of, so 2e to the minus t squared, let's put it there. Minus s squared in this case. And yeah, and so we have the integral that we can do one way or another. It's e to the minus s squared, s to the p minus 1. Looks like a gamma function integral, but we can do it by parts. By parts, and I sat here and I done it by parts offline. I won't bore you with these details by parts. So you do p times by p half times by parts or something like this, and the result is p times p over 2 minus 1 factorial. So every time you do it by part, you multiply by something, and it accumulates as a factorial. Do it yourself. Okay, all right, let's see. So are we in good shape or not? What do we want? Again, what's the right answer here? Root p. Okay, for the LP norm. The LP norm is pth root. So we should have something like root p to the power p. So our goal is to have root p to the power p. Well, we're almost there, I think. Because if we, yeah, each of these terms is less than p, I think. Okay. Yeah, each of these terms is less than p, obviously. And p factorial is less than p to the, no, that's not a good way to do it. Okay, I wanted to say something like this, p to the p over 2 minus 1. Yeah, there's p half minus 1 terms here in the factorial, and each term is obviously less than p, so that's obvious. So p to the p over 2. Yeah, good. We're done. This means that the LP norm, to get the LP norm, you just take the pth root of the result. Take the pth root, you get p1/2, and that's exactly what we need, root p. Check mark. Yeah. Questions on 1 to 2? How do you get from tails? If you know some information about the tails, then you automatically know the information about expected value and all the moments. And okay, so that's how we do it by the integral identity. Good. Now let's just think 2 to 3. How would we do that? If we know information about all the moments, so you know something like x to the p, then you want to bound a quantity like this.
Maybe Taylor series.
Yeah, exactly. Taylor series. That's about the only thing I would do too. The exponential is highly nonlinear, and so how do we handle nonlinear functions if we have polynomials, right? It's like we know information about the polynomials of x, and we want the information about some nonlinear function of x. Well, of course, Taylor series expresses this in terms of polynomials. That's what it is for. Yeah, exactly. So let's do it. Will it be boring or not? I don't know. Shall we do it? Oh, let's do it. Because now we kind of know what to do. 2 to 3. Again, let's forget about this K1, K2 stuff. Let's just say that we have this. So we know that expected value of x to the p is less than p to the p over 2. And we want e to the x squared. And again, let's see, sorry, let me just look. We want divided by k3 squared. So I don't know what it is, but probably the larger constant I put here, the easier will be to do it, right? Because it will get it smaller. So let's divide by 100 and let's see if we succeed with that. And if 100 is not enough, we'll later can raise it a little bit more. But let's see if that's enough. Taylor series. Okay, what's Taylor series for the exponential? For e to the x, that's going to be what? Sum of
x to the nth over n factorial.
Yeah, it's x to the n. Let's say p. Let's say x to the p over p factorial. Exactly. So this is a Taylor series for e to the x, and our little x here is x squared over 100. So it's going to be this x squared over 100 to the p over p factorial. So this is Taylor. This is by Taylor series. Yeah, good. Then we can, again, the added benefit to doing Taylor series is now that we can swap the integration and summation, again, by Fubini theorem. We can do that, and we get the sum on the outside, expected value of x to the 2p, divided by, what is it, 100 to the p factorial down there. Yeah, okay. Now, we know this. So what is it going to be? The moment. This moment is then bounded by, so we apply it for 2p and not p. So it's 2p to the power p. Yeah, it's just a change p to 2p. Cool. Okay. Let me think. Is everything all right? I think it's all right so far. Now I want to bound it somehow from 0 to infinity. And we have, well, p factorial stands in our way a little bit. P factorial is not a good thing. So we need to bound it below. So for the bound above, I need the bound denominator below. So p factorial by Stirling's Stirling's approximation is, remember the first approximation to the truth is that p factorial is like p to the p. approximately. The second approximation to the truth is that it's p over e to the p. That's the second one correction. And then you can have more corrections, but I think that is true by Stirling. Okay, so what do we have here? We have, aha, yeah, so p will cancel here. P to the p will cancel, that's great. And we're left with 2e, e will go denominator, 100 to the p, something like this. Yeah. Perfect, I think it's good. It's good, this is a very small number here. Maybe it's less than 1/10. Small number to the p. So for p0, that'll be the leading term here. It's the geometric progression. The leading term is 1. For p equals 0, you have a 1. That's the first term, right? The next term will be like 1/10 or better. And the third term is 1/10 squared and then 1/10 cubed and so on and so forth. And I think it's going to be less than 2. So if you sum this up, 1 plus 1/10 plus 1/100. Just as we claimed, so that's good. Yeah, check mark. Yes, we proved this by Taylor series. Any questions? We're good. Okay, cool. So we're going through this series of tools that will be useful for you, I hope, elsewhere. So integral identity here, Taylor series here. Okay, from 3 to 4. From 3 to 4. Yeah. Any suggestions? This one is difficult.
This looks like a good case for Cauchy-Bunyakovsky.
Yes, except, unfortunately, except Cauchy-Bunyakovsky or Cauchy-Schwarz will not take into account the expected value of x itself. Cauchy-Schwarz and Cauchy-Bunyakovsky, it's always about like taking absolute values in the right-hand side. So how do we incorporate that? Because we know without that information, the result is false. And so that could be a problem. I do not know how to do that, unfortunately, by Cauchy-Bunyakovsky. So
probably like the fact that the mean is 0 means that the expression in the third is almost variance, and apply some inequality for variance.
yeah, that could, yes, that could be. I do not know how to do that exactly, but that's promising. You can, yeah, I agree. If you can succeed with this proof, let me know, because right now I'm not so part of this is part of the Sub-gaussian lemma. They were developed in different times, and part of them I proved and part of them other people proved, and this is a part I think that I proved some time ago, but we don't have a very good way of doing it. So maybe by variance. Historically, the first proof that I thought was just to look at Taylor series, right? E to the x squared and e to the x. The Taylor series will have first term, which is 1, in both series. So that's good, they're comparable. The second term will be expected value. Taylor series for the e to the x. That's 1 plus x squared over 2 and so on and so forth. The second term will be x, and if you take expected value, we'll get, sorry, if you expect value, you get expected value of x, which is 0. So the second term will vanish. And in here. And then the third term and so on and so forth, they will be comparable because this one will skip a term. E to the x squared, if you, that's what we did actually here. E to the x squared has only even terms in it. And e to the x has all the terms in it. And so you can just compare them pair by pair. So this is ugly. So you can do that. So a slightly better proof was suggested later, and this is what we'll do, is to directly compare e to the x and e to the x squared and x. Again, remember, we need x here because of the expected value is 0. We need to incorporate that. So if you, that is actually true for all numbers, this inequality. So do it yourself. Either you do it by Taylor series, like I explained, or you can just notice the essence of it. E to the x is a function that goes like this. So it has this derivative. E to the x squared is a function like this. It has this derivative. So having x here is meant to correct the derivative. It is, derivative of this is 0, derivative of this is 1, derivative of this is 1. So now if just it matches the derivatives, fine. So locally around 0, we're good. Globally, if x is large, then e to the x squared, of course, it's faster. It goes to infinity faster than e to the x. So we're also fine. And so that's why this inequality feels okay. Yeah, okay. So now if you prove it, then things become easy, kind of. So we use it for, let's say, lambda x instead. That. Take expectation on both sides. Like this. By assumption, this is 0. And so we kind of we already have this inequality that compares this MGF to this. This is exactly what we need. We want to derive from here, we want to derive the bound on MGF, and this is a bound. Okay. Now I would like to take lambda squared outside. So this is less than e to the, this is probably the most difficult part of this proof, e to the x squared raised to the lambda squared. Why? Why can I do that? There's like a power of lambda squared inside, and now I'm claiming that I can take it outside. What can ever allow me to do that, for example?
Something like Jensen.
Yeah, something like Jensen's inequality, or maybe LP, because raising to the power is like LP, just the fact that LP is increased. Yeah, so you're right. So this is Jensen's inequality. And it works if lambda is, I think, is greater than 1. Lambda is smaller than 1, actually. Yeah, then it is convex. So we have e to the lambda x is less than, sorry, just continue this. This by assumption we bound, so this is e to the, this is smaller than 2 by assumption. And the result is that it's smaller than 2 to the lambda squared. So e to the lambda squared log 2 or something like that. Which is what we need. And let me show you what we needed. We need to bound the MGF this way, something times lambda squared. So we apply Jensen's, this mysterious inequality plus Jensen's inequality, and we're fine. But guys, I'm not happy with this proof, right? It uses 2 weird steps, and it only works for small lambda, and for large lambda, you need something else. So this is probably the most bumpy part of this road. And if you know a better and a more clean way to prove this, let me know. And if you have a very nice proof that's nicer, I will include it in the new edition of the book, because that proof was actually suggested by someone like you when I taught the course. Okay, so from 3 to 4. Good. Any questions? Good. And finally, from 4 to 1, completing our journey of this lemma is this way back. So if we know the MGF of this, then we know the tails. Okay, from this to this. Well, we already did that, actually. Or kind of did that. That was the way we proved Höfding's inequality. That's an MGF method itself, right? You bound the MGF, and then you deduce the tails. So let's do it. Just the usual MGF method. If we are interested in the tails, let's say one-sided tail first. E to the lambda x, you multiply by lambda, we exponentiate. I'll go a little bit faster on this because we did it already a couple times. And then we use Markov inequality. Markov inequality. Then we use the assumption on MGF that it is bounded by something like lambda squared. Again, I skipped the constant here, so lambda squared. This is by assumption 4. And we get e to the lambda squared minus lambda t. And lambda is arbitrary, so we can minimize in lambda, and the optimal lambda is actually t over 2, and I just did it myself, just take the derivative. And so we get e to the minus t squared over 4, which is a Gaussian tail, check mark. Good. This is just like a Höfding's inequality. Good, proved. Proved. So this is our lemma, and it says again that all of these Sub-gaussian properties are equivalent to each other. All of this information, however different it may look like about the tails and the moments and MGF and everything, is actually the same story. And that story we call Sub-gaussian.
But also, it seems that
let you go first.
Okay, Evgeny, or Pablo, yes.
yeah, my question was that if expectation is not 0, we still need somehow to connect 3 to 1, or
Yeah. Oh yeah, we didn't prove that. Yeah, you're right. 4 to 1. Yeah, we didn't do that. But no, actually, sorry. If yeah, so if we proved from 1 to 4 and for 4 to 1, yeah, we need kind of another cycle there. But
okay,
good catch. It's in the book. I proved it, and we will not go in detail here. It's going to be boring. Yeah. And someone else was asking a question.
My question was exactly the same.
Okay, good. Yes. Yeah, let's skip that. Good. So here's the lemma. Okay, so qualitatively, we know that all these properties are equivalent to each other. Now, next good step of the story is to note that quantitatively, they're also equivalent to each other, which means that all of these constants, not constants, all of these parameters, K1, K2, K3, whatever, this is boring things, they also are equivalent to each other within a factor. So maybe K1 maybe like is twice larger than K2, and K3 may be twice smaller than K4, but other than that, they are all equivalent. They all have the same magnitude. And that is important because we're headed into the quantitative world now. So the remark, it wasn't clear from the proof, but if you do this proof, the same proof that I gave, it will be crystal clear that all of these constants, all of these parameters, K1, K2, K3, K4, are all equivalent up to absolute constant factors. So for example, I don't know, something like K2 is less than 3K1, maybe. I don't remember the exact factors, but for any pair there's like that. So more formally, it's Ki is less than some constant Cij, Kj. Okay, good. Okay. But then something remarkable happens. If all of these quantities are about the same, then they capture the same elusive quantity, the same kind of property, right? So they all capture something about the random variable that is the same. So they capture the same quantity, and we just call that quantity the Sub-gaussian norm. The Sub-gaussian norm. To be precise, we can choose one of them and call it Sub-gaussian norm, and the rest will be equivalent to it. But why norm? It's absolutely not clear that the best K1 here will define a norm, but the triangle, it's a notion of the length, right? The triangle inequality will hold or anything like that, or this. Absolutely not clear, but it is true. Let me ask you guys, why does any of these things define a norm for a random variable? And remember what norm is, right? It's all the triangle inequality, homogeneity, and stuff like that. What do you think? Does any of it ring a bell in your head? Yes. This maybe?
Some of this is Orlish norm.
Mm-hmm. Which one? Which property you're talking about? Third, yes. Third property. This property looks like Orlish norm. Exactly. For the Orlish function e to the x squared or something like that. Yes. So property 3. And that's why we actually studied Orlish norm, because that's a way to define it here. So property 3 says that there is a constant, there is, I don't know, K3, so that this happens. So that means that, let's say, K3, so that what happens? Remember the Orlish norm, where we have some function called Orlish function, should start at 0, end at infinity, and the best constant for the best k is called the Orlish norm. That's actually norm. Okay, and we have function that's e to the x squared. E to the x squared does not quite start at 0, so I need to move it down. And then subtract 1 from both sides. Okay. So psi of x is e to the x squared minus 1 is an Orlich function. Okay, is it clear? So I just subtracted 1 from both sides. This makes the left-hand side the Orlich function, the psi2 Orlich norm, and this is exactly the definition of the Orlich norm. Perfect. Actually, let's call this psi2. That's a standard notation, meaning to emphasize the x squared part of it. So property 3 is just saying that x is an Orlich random variable. And the smallest K3 is the Orlich norm, the psi2 norm. So it's a norm. Yay. Again, the summary of what we said is that the best K3 you can put here defines the norm for a random variable. And all the others, K1, K2, K4, they're equivalent to it, up to a constant. So for all practical purposes, you can think they are norms too. Perfect. So the summary. For this, that all of these Ki's are equivalent to each other and to this. Which is called the Sub-gaussian norm. That's it. That's the end of the quantitative story now. So qualitatively, these effects are all equivalent to each other. Quantitatively, they capture the quantity, which is a Sub-gaussian norm. So I'm not sure if you want to do it like I will do now, but I will now go through this lemma, and I will replace all these Ki's by the Sub-gaussian norm. So K3, I'm replacing it with a Sub-gaussian norm like this. And K1, for example, I can do that too, but maybe up to a constant because it's equivalent up to a constant. And K2 too, up to some constant. And K3 is done, and K4 too, up to some constant. Okay, is it formally okay, clear? Yeah. Okay. This can get complicated already. Oh my goodness, all these formulas. What you should think about in my brain, it's helpful for me to do this. Previously, before this course, we knew about how do you capture the size, the magnitude of random variables. Well, there's mean and there is expectation and there is variance. The variance measures the spread, but it only measures the average spread. The variance only measures the kind of the average spread of x of the expectation. It doesn't really say how exactly it goes down, whether it goes down polynomially, exponentially, that doesn't capture anything. What we have here is we kind of boosted this knowledge. We made a new concept that's called a Sub-gaussian norm, and you can put it in the same part of your brain where the variance is. It also measures kind of the spread, the overall magnitude of x, but it captures it in many ways that the variance cannot do. So it's much more informative than just the variance. How is it informative? The variance only tells you about the second moment, basically, right? The variance is something squared. And the Sub-gaussian norm is telling us about all the moments. First, second, third, 17th, whatever. The variance can only give us Can it give a tail decay? Yes, Chebyshev, right? Chebyshev's inequality gives you something like this. But if you know the variance, the decay will be only like minus t squared, 1 over t squared. Remember Chebyshev? In the right-hand side, there is 1 over t squared. Nothing better. Sub-Gaussian gives you exponentially, actually super exponential decay. So that's how it is better. And the variance can never give you anything on the moment generating function. It's too weak to capture that. But Sub-Gaussian can. So it's variance, but on adrenaline. It's variance that gives you a lot more than kind of variance-like notion, variance proxy, a cousin of variance, which is much, much more powerful. And that is why we use it. That's why we actually introduce it, because it gives us much more information. And yeah, and then next time we'll use it. We'll just prove general Hoeffding's inequality, let's say, for any Sub-Gaussian, not just Bernoulli, just for a kick. Okie-dokie. That's all I have to say. Any questions? No questions. Okay. You're still good? You're still following this? Yeah, not too technical.
So I have a question. So this Subgaussian norm allows us to kind of compare the variables in the Subgaussian class, right? The random variables. But for each norm, we have a class of random variables that kind of have this norm. Is this kind of a wide class? So basically, can we from norm deduce the distribution of the variable in some case, or it's
by the norm, you mean the Sub-Gaussian norm?
Yes, yes.
So what's your question? Can, for example, from the norm, we deduce what?
The distribution of the variable is this still a wide class of distributions that will have a certain value for the Subgaussian norm? Yeah,
that's a great question. Well, first of all, we do not want to deduce a distribution, right? Because if we did, that means that there is just one distribution for which, you know, we can only...
normal is just one distribution, but it's so great. We talk about it all the time.
Okay, I'll take it back. Yes, maybe you're right. But what we can deduce about the distribution from the Sub-Gaussian norm, that is exactly the content of this lemma, right? So we can deduce the moments, we can deduce some bounds on the tails, we can deduce something on the MGF, but we can deduce it only the upper bounds. Because if you take a Sub-Gaussian, again, take a Sub-Gaussian random variable, multiply it by 1/10, it's still a Sub-Gaussian, right? It's better, even better, because all these bounds are the bounds above. So up to this kind of a, what do you call, like an inclusion, up to this monotonicity, right? If you multiply by 1/10, you get it better. We can deduce a lot about the distribution, right? The upper bounds, but not the lower, never the lower bounds. Because, for example, 0, the constant 0 is a Sub-Gaussian random variable. For the obvious reason, if you substitute x equals 0, you will get everything is true. Right. That said, the class is still very wide. So, for example, plus or minus 1 with probability 1/2 each. Or actually, Bernoulli, yeah, just Bernoulli with any Bernoulli. Yeah, it belongs to that, obviously. Why?
Actually, anything in discrete distribution is Subgaussian. No.
Discrete with
Any
finite
discrete distribution.
Finite.
Finite, yeah.
Finite, yeah. For example, in the homework, you'll prove that Poisson is not Subgaussian, although it's discrete, but finite, yes. Yeah, anything bounded, right? If you have a distribution that always takes values between let's say, -10 to 10, any of it, Subgaussian, perfect. And Subgaussian norm is bounded by 10, just like the variance. So yeah. So it's a pretty wide class, actually. All bounded random variables are there, and the normal is there too. So it could be very discrete, could be very very continuous, and that's why people like it. It's still wide, but it still gives us a lot of information that you can use. There is let's say there is a related notion of stochastic domination, and that's, let's say x is stochastically dominated by y if probability that x, let's say the tails, probability that x is greater than t is less than probability y greater than t. Should I say for any t, or is it possible? Yeah, I think it's possible like that. I think I'm doing it right. So in principle, you can think of this as a stochastic domination thing. A random Sub-Gaussian random variable is a random variable that is stochastically dominated by the Gaussian, but not in this exact sense. Like, because we allow some room here. Right? There's 2 here, there is constant here, so we just say, guys, this is too much. Maybe we should do like 2, and then here's maybe t over 2. So. But if you ever need it in economics, that's pretty popular, the notion of stochastic domination. We just have an approximate version of it, more flexible version of it. Yeah, good questions. Any other question? Good. Okay. All right, guys. I'll stay on. I'll drink my tea, and you have a good weekend. Stay safe, and we'll see you on Monday. Don't forget to turn in your homework as usual on Friday. So. And if you need, wait. Oksana, do you have a minute or two?
Yeah.
Yeah.
Can we stop recording?
Oh yeah, I forgot. Sorry, we should have stopped way before.